record, share screen with you guys. All right. At any point in time, if you guys have a question or anything like that, feel free to unmute yourself and fire away. You don't need to wait and use the chat, but whatever works for you. I'm going to turn my camera off because when I flip my computer around so I can write on it, I don't think you guys want to just sit here and stare at the ceiling of my room. So we'll get started.
Wait,
so the first
question.
Yeah, fire away.
So I didn't realize that there was quiz number 5. It was like due before the test, and I didn't see it. Is it be okay if I did quiz 5 and then I got like partial credit for it?
No, I okay, still do it, but I mean, as long as you're not missing a ton of quizzes, you should be fine.
Okay.
Yep. All right. So we're going to actually do 2 sections today. The first section we're going to do is 4.1. We are skipping 4.2 altogether. So feel free, if you are curious about it, to go through and read that section on your own time, but we're not going to do it in class at all. So feel free to do that. 4.1 is about related rates. I really like this section for kind of a nice kind of towards the end of term. It really brings some things in, and what it really does is it brings in some of your guys' kind of equation creating abilities, which is something that we all could use and practice with. And so the hardest thing with this section is creating the equation, finding the equations that you need to use. The actual derivatives that we're going to be taking are going to be fairly simple. They're going to be using implicit differentiation to do it. And so they're pretty easy to do. Hopefully you guys can kind of be pretty comfortable with it. So let's just get started. We don't really need to do anything crazy to get started. I do want to drag an image in here for you. Here. Okay. Let's just do this. All right. So when you are using the idea of related rates, kind of what we want to do is what we've got listed here. So these are in the textbook, so you can find these in there. These aren't any novel ideas here. We need to assign variables or equations to the interested things that we need in the problem, the things that are involved, whether that's, like if it's a ball, the radius, the volume, and stuff like that. And this isn't necessarily some crazy thing we're creating. There are a lot of times it's, height, radius, volume, circumference, area, things like that we already kind of use those first letters for. Once we have that, if we can get a nice picture drawn so we can have a good visual of what's going on. And then from there, we want to try to figure out, in terms of the variables, what information we know from the problem and what we're looking for. Once we've found that, this says using the chain rule, but it's using implicit differentiation is really kind of what it's doing. Using implicit differentiation and chain rule to take the derivative of both sides of whatever equation it is you're trying to find, substitute things in and solve. Sometimes it's really simple problems. Sometimes it's just very simply following that process. And sometimes we have to find extra things and kind of do back. And we'll do a few examples in this section so we can kind of get a good feel for it. So the first problem, I'll write it out. There's really no new big profound theorems or anything in this section. It's really just kind of an application of some things. So if air is being pumped into a large spherical balloon at a rate of 150 cubic centimeters per second. how fast is the radius changing when the radius is 5 centimeters, and also when the radius is 10 centimeters. So obviously I can't see you guys. So if I move too fast, if I slide around, please unmute yourself and say, hey, well, go back, and I'll slide back so that I can see, because I can't see when you guys are, writing and paying attention and stuff like that. So, so what this problem is doing is it's giving us information about the volume of this balloon, but it's asking us questions about the radius. And so this is what this whole chapter goes off of, is its related rates. So we're able to relate the ideas in here, the values of radius and volume, they're related to each other. So we're able to create equations that relate one to the other, and then we're able to use the information about one to find information about the other. So the first thing is we want to write down what we know, right? And so what we're told here is, first of all, it's a spherical balloon. So, right, we all know if you blow up a balloon, it's not perfectly a sphere, but we're going to, imagine we're in a nice, perfect world, and this blows up exactly spherical, so it's nice and perfect. We know that the volume of a balloon is equal to 4/3 pi r cubed. And its units are going to be in units cubed, in this case, centimeters cubed. And now if we have this volume is changing with time, we can create essentially sub-functions for volume and radius based on time. And then we can create a relationship that we would say is V of t is equal to 4/3 pi times r of t cubed. We'll add on where V of t is the volume of the balloon. The balloon after t seconds. And r of t is the radius of the balloon after t seconds. So hopefully those two things aren't crazy shocking for you, right? But that's just converting this volume formula, which is just the volume of the sphere, into this kind of formula for the volume based on a specific time. Now, what else do we know from this problem? What we know is that V prime of t is equal to 150 cubic centimeters per second. We know that the volume that is being pumped up at a rate of 150 cubic centimeters per second. So that means that our volume is changing by that. So now what I can do is I can take the derivative of both sides of this V of t equals 4/3 pi r of t cubed equation. We can take the derivative of that with respect to t on both sides. And so we end up with V prime of t equals 4/3 pi times, now to take the derivative of r of t cubed, we use the chain rule. And so we get 3 r of t squared times r prime of t. Now that simplifies nicely, right? The 3 and the 3 cancel out. We end up with just 4 pi times r of t squared times r prime of t. Does anybody have any questions about what we did there, how we took that derivative? Does anyone have any questions? Give you guys a couple seconds to write that down and think of questions.
So for this one, we wouldn't have any like dt over dx or anything.
So with like the idea of implicit differentiation, right? When we did things like y equals 3xy kind of stuff like that. What we're essentially doing here, so when we did stuff like that, we'd end up with things like dy dt, right? That is like our v prime of t and our r prime of t. That would be like, so v prime of t is dv dt, and r prime of t is dr dt.
Oh, so, okay, just a different notation thing.
Right. So we're just using the kind of the apostrophe notation for derivatives instead of that Leibniz notation, to allow us to just kind of use this a little simpler. But it works the same way, right? Because what we do when we do implicit differentiation, right? If we have something like this, we treat that y, essentially what we're thinking of y, it's some y of x. And that's why when we take the derivative, we get a dy dx. And so here we're just using function notation right off the bat instead of using just random variables to allow us to do that. If we use the base formula, so this one here that I put in the box, if we used that formula, we could use implicit differentiation, and then we would get like the derivative of v is just 1, and then we get dv dt. And then we would end up with 4/3 pi times 3r squared dr dt if we did it that way.
Okay, thank you.
Yep. So with what we have here, okay, we can solve, right? Remember the question is asking us how fast is the radius changing when the radius is 5 centimeters and when the radius is 10 centimeters. So the question is asking, so the problem wants to find r prime of t at specific radii? I don't know. Plural of radius. Yeah. At specific points in time. We'll say at specific times. Now, we're not given times as in values of t, but we're given times as in the time at which the radius is the certain value. So using this and the equation we just took, we get that r prime of t is equal to v prime of t divided by 4 pi times r of t squared. Everyone see how we did that, right? Just dividing by the 4 pi r of t squared. So now we can answer our question. It's really, at this point, it becomes very simple. We plug in the fact that v prime of t is 150 cubic centimeters. And so we get that this is equal to 150 divided by 4 pi and r of t squared. So then if the radius is 5, right, that means that r of t equals 5. R prime of t is equal to 150 divided by 4 pi times 5 squared. Now, if we use our calculators, because I know all of us love to do that kind of math in our heads, and we do 150 divided by 4 times 5 squared, so we basically ignore the pi for a second, what we end up with is a reduced fraction of 3/2. And then we just keep our pi in there. So we get that r prime of t, when the radius is 5, is 3/2 pi, which is approximately equal to 0.4777 centimeters per second. Any questions on that? Does that make sense?
Yeah, that makes sense.
Everybody else? Awesome. Now, if we do the same thing, right? We say when R of t equals 10, because that was the second question, then R prime of t is 150 over 4 pi times 10 squared, which ends up being 3 over 8 pi. Which is about 0.119. So this is the basic idea. This is probably one of the simpler problems that we would deal with related rates, right? And so notice the biggest thing that we need to do is we need to find some equation, I'm going to zoom out a little bit, that equates our variables. So in this case, our variables were volume and radius. And so we needed to find this equation. So the important equation here was this one. Okay, this was our big important equation. Because that is our equation that relates these two things, which allowed us to do everything else. Okay. Any questions on that problem? Everything makes sense. So in that case, let's jump to another problem. Now, this problem is a little bit more complex in that there's some extra math that we need to do. None of it is things that you haven't done. None of it is anything crazy. It's all things that I could have asked you to do in Math 111. Heck, some of it's things I could have asked you to do in Math 95 even earlier. So a 20-foot long ladder is leaning against the wall. Now, anytime we have situations like this, unless it specifically says anything different, it's always safe to assume that that wall forms a right angle with the ground for the sake of our problems here. In real world, we needed to verify that, but for all our problems here, let's assume it is. So if the base of the ladder is sliding out at a rate of 2 feet per second, how fast is the top of the ladder sliding down the wall when the top of the ladder is 12 feet up the wall. All right, so this is our problem. Now, this is something that we could all see happening, right? Hopefully we can envision a ladder being on the wall. If it starts to slide out and fall down, it goes. The first thing to do here with a problem like this is to get a picture, because there's nothing better than having a nice visual picture representation of what's going on with these problems. When we deal with anything that we can get a visual of, it always helps our understanding. It helps our labeling as well. So we've just got the good old classic ladder on a building, right? Go to right angle here. Our ladder, we know, is 20 feet. Now, what we don't know is the rate at which it's falling, which it's sliding down. We know it's the rate it's sliding out. So I'm going to say that this here is D. It's the distance from the base of the ladder to the wall. And then the other side here is going to be H, our height of the ladder from the ground up. Now, both of these, because our ladder is falling, we can create these both as a function of time. So we can instead just call it D of t and H of t. What I know is that the ladder is sliding out at a rate of 2 feet per second. So that tells me that d prime of t is 2. Now, we need to come up with some sort of an equation that equates d of t with h of t. What could I use to equate d of t with h of t?
The Pythagorean.
Perfect, right? Our Pythagorean theorem, right? Which if you remember, right? If we have a right triangle, we have our A, B, and C. It says that A squared plus B squared equals C squared. So in this case, we get that H of t is equal to the square root of 20 squared minus d of t squared. So this question is asking us how fast is the top of the ladder sliding down the wall when the top of the ladder is 12 feet up the wall? That's the question. So the question is asking about h prime of t. So that's why I created the equation in forms of h of t instead of d of t, right? I didn't want to say d of t equals square root of 20 squared minus h of t, which is true, but I'm not worried about what the d prime of t is. I'm worried about what h prime of t is. So that's why I created the equation in that way. So now we need to take the derivative of h of t. Now to do that, we use chain rule a couple times, okay? So the first thing we have is essentially the square root. So if I wanted to break this out and kind of show every different thing that we have, right? I could say f of x, square root of x, g of x is 20 squared minus d of t, or minus x squared, and then h of x is just d of t, or d of x. And so we're composing all of these together to give us this h of t function, which I used h of x here, so I'm going to change that. We'll just call that j of x. D of. So we compose these together to get what we want. So we need to take the derivative of each of these. And so what ends up happening is, if you guys remember the derivative of square root, we want to think of converting that into its exponent form. So we think of this as x to the 1/2. Using the power rule, we end up with, so h prime of t. So we end up with 1 over, and then we get 2 times the square root of 20 squared minus d of t squared. So that right there is the derivative of f of x evaluated at g of j of x here, basically. And then we multiply this by the derivative of what's under the square root. So the derivative of 20 squared is nothing. Then negative d of t squared gives us times negative 2 d of t. And then times the derivative of d of t, so we get d prime of t. Is everybody with me on this so far? Does everybody follow that derivative? Give me a second to write it down and let me know.
Yeah.
Okay. If you aren't sure how I got that derivative, please ask now and I can go through it slower and I can piece it out, or talk to me later. We will have a break after this section and before the next that we will be able to, if you want to ask then, we can go over it. So the question is asking us to find, remember, how fast the ladder is sliding down the wall when the top of the ladder is 12 feet.
We have a question.
Yeah, what's up?
That d prime of t, could you go over where that came from? Is that just the I forgot what it's called. But like, could you go over where it came from? Yeah, the implicit.
That's it. Yep. So that's just the derivative. So this first piece here is essentially it's f prime of g of j of t. Right, so that's that bit. Then this is g prime of j of t. Multiply. And then the d prime of t that is the j prime of t.
Okay, so it's just a chain rule 3 times.
Yes, it's just chain, chain, chain. Yep.
Okay, thank you.
Perfect. So problem wants h prime of t when h of t equals 12. Now, the problem is h prime of t, that formula, right? It has two different unknowns in it for us. It has d prime of t and d of t. So we already know that d prime of t equals, if we look back to the very beginning, d prime of t equals 2. Because we were told in the problem, the base of the ladder is sliding out at a rate of 2 feet per second. So we already know that d prime of t equals 2. So to find h prime of t, now I'm writing all this out because this is something that, this is just what I'm saying to you guys. You don't have to write all this if you're just listening, but write it if you want. To find h prime of t, when h of t equals 12, we need to find d of t. So what that means is we have our triangle. This is 20, this is 12, and this is d of t. So we need to find out what that equals. Okay. And very simply, using the Pythagorean theorem, d of t equals 16. If you don't believe me, please grab your calculators and find it yourself. So h prime of t. Now I'm going to bring the blue highlighted and the orange highlighted pieces into the numerator. And so we end up with -2 d of t times d prime of t all over 2 times the square root of, oh, come on. Of 20 squared minus d of t squared. Now we know d of t equals 16, and we know d prime of t equals 2. So doing some basic cancellation. So first of all, our 2's go away because everything's being multiplied here. So then d of t is 16 times d prime of t, which is 2, divided by the square root of 20 squared minus 16 squared.
Is the negatives go away?
No, sorry, negative is still there. So we can just very simply use our calculator to do all of this for us. We have negative 16 times 2 over the square root of 20 squared minus 16 squared. And that gives us negative 8 thirds. And that would be feet per second. Now, a quick check, right? And this is something that is really easy to make a mistake on. Like you saw, I dropped that negative, right? This ladder is falling. So the rate of change of the height of the ladder up this wall, would that be increasing or decreasing?
Decreasing.
Decreasing. And so this derivative should be negative. So that's always a good thing to do, right? Little checks like that, because the most common mistake I see when you understand the material, but you make a mistake is usually dropping a negative or making a positive a negative, something like that, changing signs. And so if you just think like, okay, the ladder's falling, so I know the derivative needs to be negative at this value. And at the end, if you end up with a positive number, be like, whoa, I made a mistake, and go back through your work and see if you dropped a negative somewhere, if you know, what happened. So any questions on that problem? Excellent. So our next problem, I'm cheating and I'm copying over. Oh, wait, no, I didn't copy over. Just kidding. That's the funnel one. So our next problem your rocket is launched. So that, as all good rockets do, it goes vertically up. There's a camera. Positioned. 5,000 feet from the launch pad. Okay. When the rocket is 1,000 feet off the ground, it is traveling at 600 feet per second. What I want to do is I want to find the rate of change of the camera's angle of elevation so that the rocket remains in focus. I'll say specifically when it's 1,000 feet off the ground. So at this time. So the rocket is launched, so it goes vertically up, so it's not at an angle, right? Again, this just tells us that we're dealing with a right triangle. There's a camera that's 5,000 feet away on the ground. And we know that when the rocket is 1,000 feet high, it's going 600 feet per second. We need to find the rate of change of the angle of elevation of the camera. So that's the angle created from the ground and essentially the lens of the camera. We need to find the rate of change of that so that it remains focused on the rocket. Any questions so far?
I have a question.
Yeah.
So just judging off the information, we know that our final derivative should be positive, right? Because the angle is increasing.
Yep.
Okay.
Great observation. So now this problem has a very similar drawing to the last problem. However, the difference here is that this problem is no longer concerned with the distance of a certain angle. Terrible triangle. Perfect. So we have our rocket ship. Fire. No, let's get some color on this fire. I've got colors. We can do it. Fire. All right. And what we have over here is we have our camera, lens. So we know we're talking about some angle. I know I have some height of the rocket, which is a function of time. This angle is actually a function of time as well. And what else do I know about this triangle?
It's 5,000 feet from the launch pad.
Right? We know that the camera is 5,000 feet from the launch pad, so the base of this triangle is 5,000. Awesome. Now, there's two more things we know. We know that when h of t is 1,000, h prime of t is 600. So what we're looking for we are looking for theta prime of t. So we're looking for the rate of change of the angle at some time. So we want to create a function that relates the height of the rocket and the angle of the camera. And then we want to take that, and if we can, solve it for either theta or h at least. That way we can use it to plug some things in. Now, we can get very simply that tangent of theta is h over 5,000. So we could then say that h is equal to 5,000 tangent of theta. Now you may be wondering why I didn't use inverse tangent to solve this for theta and get a theta equation. And the reason very simply comes down to the fact that the derivative of inverse tangent is not nice. I don't want to do that. So I'm going to stick with this because the derivative of tangent is just secant squared. And that's a far easier thing to deal with than what we're looking at here. So we now have an equation that relates these two things. And so now changing it from just these arbitrary variables to their variables as a function of time, we get h of t equals 5,000 times tangent theta of t. As we take the derivative of both sides, we get h prime of t is equal to 5,000 times secant squared of theta of t times theta prime t. Now, depending on what you're looking at, people don't necessarily like functions of like theta of t. And so some people would just leave it as theta. And then instead of saying theta prime, they would just say d theta dt. That's really up to you what your preferences are. Mathematically speaking, it's equivalent. So we're trying to find, so we want to find theta prime of t when h equals 1,000 feet. We know what h prime is here, okay? So we can use that to give us 600, 5,000 secant squared of theta of t times theta prime of t. Now, the problem is, what do I do with this secant squared? Well, keep in mind that secant squared, or that theta of t, is a fixed value at this fixed moment in time, right? We're looking at this singular moment in time when h is 1,000. So when h is 1,000, theta is a single value. So we don't have to worry about it being, all of these possible values. And so we need to find what secant squared is. So we need to find secant squared of theta when h is 1,000. So I'm going to draw my triangle again. Okay. What if I come up to this one? Copy. Paste. Perfect. All right. So what I have here is I have 5,000 on this base. This is 1,000 at the moment we're looking at. And this is our theta. So looking at this, what is secant squared of theta? This is a lovely Math 112 problem. So in general, secant of theta is what?
1 over cosine.
Yes, but let's think about the sides of the triangle. You're not wrong. So it is hypotenuse over the adjacent side, right? Because cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So that means we're missing our hypotenuse. We need to find out what this is. And we know very simply that the hypotenuse is the square root of the sum of the squares of the other sides. So it's the square root of $1,250,000. And all of you guys know that this is a common one. This is just 1,000 times the square root of 26. So I don't want to get an approximation. I don't want to use a decimal version of this at all. I would be fine if you left it as the square root of 1,250,000, or if you got it down to 1,000 root 26. Doesn't matter. Either one would be totally fine. So that means that secant squared of theta is our hypotenuse, which is 1,000 root 26 over 5,000 squared. which I did the math, I crunched the numbers. That to be 26 over 25. Any questions on that? Okay. So if we go back up and look back to what we were looking at, right? We had this. So using that, okay, we get 600 equals 5,000. And then instead of secant squared of theta of t, we have 26 over 25 times theta prime t. So after some hard mathematics, multiply our 5,000 times 26 over 25, 600, 5,200. Prime of t. And we end up with theta prime of t was 3 over 26. And now this is angles moving per second. So this is radians per second. So essentially, when the rocket is at a height of 1,000 feet, our camera angle needs to be moving at 3 radians every 26 seconds, or 3/26 of a radian every second. Any questions on that?
If you went in the beginning, if you took the inverse tangent and then would you come back if you did the whole process, would you come back to 3/26?
Yeah, that would be a way to do it. You would end up with the same answer. It's just a far less friendly derivative that ends up with some far messier pieces. So what is the derivative? Just to kind of make a note. I'll zoom in. Oh, you guys right now, look up in your notes. What is the derivative of the inverse tangent of theta?
It's 1 over 1 plus theta squared.
So 1 or 1 plus theta squared. Yes. So doing that, we would have had theta is equal to 1 over 1 plus h over 5,000 squared. And then taking the derivative of that would have been very messy. Wait, no. Oh, what is it? So then theta, so you can kind of see what this would look like, equaling inverse tangent of h over 5,000, and theta prime of t be 1 over 1 plus h over 5,000 squared. times 1/5,000. And then trying to deal with that, you should end up with the same situation, but it just kind of becomes a little messier. Plus, the other way works some things that I wanted to show you, because there's other problems that you don't have as easy of derivatives of inverses. And so using this way is a little more direct. You can do this with using inverse trig functions, as I said before, but the most complicated part of this part was figuring out what's secant squared. That makes sense?
Yeah.
All right. We have one more problem on this, and then we will be done with 4.1. Our last example is water is draining out of the bottom of a cone funnel. Cone-shaped funnel. At a rate of 0.03 square feet per second. Height of the funnel is 2 feet. And the radius at the top of the funnel is 1 foot. At what rate is the height of the water changing when height of the water is at 1/2 So what we have here is water draining out of this cone-shaped funnel at a rate of 0.03 square feet per second. Sorry, not square feet, cubic feet. That's not right. Since we're draining out volume of water. We know the cone's shape is 2 feet tall and with a 1 foot radius. So that tells me that the height of the cone and the diameter of the cone are the same. And we know, and we want to know what the rate, at what rate the height of the water is changing when the height of the water is 1/2 foot. So I'm going to pull in, I have a picture. This is what I cheated and copied from else. Bigger. So here we have our relationship going on of our cone. We're letting H be the height of the water, R be the radius of the water at that specific height. We do need to know the radius of the water's height or at that height, but that's going to be something we'll be easily able to deal with in just a minute. So I want to give you guys a second to write this down, get this picture drawn. Let me know when you guys have it. Just either give me a thumbs up or a unmute yourself and just say, hey, we're all good. All right. Does everybody understand what this question is asking us to find? So I'm going to take you guys' resounding silence as a yes. So what this problem is asking us to find, right, is the rate of change of H, right? So it wants us to find, so find H prime of T and H of T is 1/2. Now we could change this to inches and stuff like that and it would still be equivalent, but I want to keep this as feet because our volume or our rate of change that we're given, the amount of water leaving is given to us in feet per second, cubic feet per second. So I want to leave it as that. So looking at this, one of the things we need to recognize is that we have similar triangles between the overall cone and this piece created by the water. That means that we can create equivalent ratios of their size. Okay. So that's going to be important, right? We know that, say, the ratio of R over H is 1/2 because the radius at some given height is going to be the same ratio as the full radius over the full height. So what I can use that to give me is that the radius is H/2, which means that the radius of time T is H of time T out over 2. Now, you may not see why I need to solve for R yet because we haven't created our initial formula, but let's do that right now. We know the volume of a circular cone is V equals 1/3 pi R squared times H. Now, for those of you who are less familiar with geometric formulas such as these, do not hesitate on homework to Google what those formulas are, right? I do not expect you to memorize these. on your final, which is the next test you'll have, I will give you, that will be in person. And so I will give you all formulas that you would need to solve any of the problems that you would need to do. Okay. So I will probably have a formula sheet that I will either give you the exact formula in the question, or I'll give you a formula sheet with a bunch of formulas and you just have to figure out the right one. So this, then we can say that V of t is 1/3 pi times r of t squared times h of t. Since the problem wants us to find h prime of t, I want to get rid of this r of t. I don't want to have 3 functions going on. And that's why I did this. So we know that r of t equals h of t. So I can replace, or h of t over 2. I can replace this. And so we get that v of t is 1/3 pi h of t over 2 squared times h of t. Which if we simplify this, so we square h of t over 2, we end up with a nice little formula. It's just pi over 12, no triangle, pi over 12 times h of t cubed. Any questions on that?
So could you go over why you substituted r of t for h of t over 2?
Yeah, the reason I replaced r of t with the h of t over 2 is so I have only 2 functions, because I don't know the rate at which the radius is changing, right? So if we go back into our problem statement, we don't know anything about how the radius is changing. We know how the volume is changing because we know that it's decreasing at a rate of 0.03 cubic feet per second. I'm looking for how the height is changing. I don't know anything about the radius changing. And so I want to get that out of the equation by replacing the radius with the height. And to do that, we used the relationship between the similar triangles. Does that make sense? So
Yeah,
let me
so
say, go ahead.
So you just wanted to find r of t in terms of h of t, or something you already know?
Correct. I wanted to find r of t in terms of either v of t or h of t, so that I can only have 2 essentially variables or 2 functions in this situation.
If you went for like a v of t, would that also work?
It would be a lot more complex of a formula, because basically you would just, so r would be equal to the square root of 3v over h.
Oh, I see. Okay, thank you.
And so, yeah, using the similar triangles is just a lot easier. All right, so we now have this. So we now know that v of t is pi over 12 times h of t cubed. So then v prime of t is, now using the chain rule, so the 3 will come out, make our pi over 12 pi over 4 times h of t squared times h prime of t. Any questions on that derivative? What is v prime of t? Who can tell me what is v prime of t? And don't say the equation I just wrote down.
Wasn't it like 0.003?
What do you think? What do you guys think? I'll go back up. I'll zoom out so you can see the problem. Might be a little small. Anyone else want to take a stab? Your answer is close. I mean, your number is wrong, right? But I know you meant 0.03, not 0.003. But that's not right. V prime of t is not 0.03.
Oh, 0.03 cubic feet per second.
I'm not being that pedantic with you guys right now. It's not 0.03. Why is it not 0.03? You're very close, but you're missing something. What is V of t? Let's start with there. What is V of t? Like, what does that represent?
The volume.
Volume. Is the volume, how is the volume changing? Because V prime of t is talking about the rate at which the volume is changing. Is the volume increasing or decreasing?
Oh, yeah, it's decreasing.
It's decreasing.
Okay.
So we know that the water is draining out of the bottom of the cone at a rate of 0.03 cubic feet per second. That means that V prime of t, the volume, the rate at which the volume of water in the cone is changing is decreasing. So that means that V prime of t is negative 0.03. So H prime of t, when H of t equals 1/2, is, well, we know V prime of t is negative 0.03 pi over 4. H of t is 1/2, so we get 1/2 squared times H prime of t. So we get negative 0.03. 1/2 squared is 1/4. Pi over 4 times 1/4 is pi over 16. Times H prime of t. So H prime of t is negative 0.48 over pi, which is approximately equal to negative 0.153 feet per second. Any questions on that?
If you go back to the original picture of the problem,
Yeah.
it was like a
Just
funnel.
let me,
and
give me 1 sec while I want to let people get this down. Does everybody have this written down? Give me a thumbs up if you do.
Yes.
All right. So let's jump back to the picture. All right, what's up?
So that little bit on the very bottom, that little bit is kind of insignificant. We don't really care about that, right?
Correct. We're just basically mathematically saying that doesn't exist. It's non-significant. We're looking at just the height of the cone itself. So.
Okay.
Awesome. Does anyone else have any questions on this problem? All right. So I have 146 right now. Let's take a 4-minute break. Is everybody good with that, or anyone need more? All right. So then let's take a 4-minute break. So at 1:50, we'll start back with our section 4.3. All right, guys, let's start back up. Share my screen again. Okay, so this section that we're going to cover now is 4.3, which is a maximum and minimum. So before we get into this, does anyone have any questions over 4.1? All right, I will take your overwhelming silence as no. So maximum and minimum with functions is something that you may have covered before in other classes. You may have just talked about. It may have been, you kind of just assume that you kind of understand what's happening. And there's two types for each, right? So if I have just some function, say like this, okay, this function here has two we call local maxima, one local minima, and one global maxima. Okay. So anytime we have this peak like this, or this dip like this, we get a local maxima or local minima. So each of those points are local maximum or local minimum. Global maximum or minimum is the either highest or lowest point of a function. So this point here is both a local and a global maxima. This point here is just a local maxima. And then this point down here is just a local minima. Why is that lower point just a local minima and not a global minima? There's no other point that, right? There's no other turning point lower than that, right? So why is that not a global minimum?
Because it tends to negative infinity from both sides.
Right. Because of our ends, they go to negative infinity on both sides. And so this is what we're talking about. We're talking about local minima, local maxima. Now, we can set some really kind of formal definitions for it. We're going to do those. And so you say, let F be defined with an interval I containing the value C then f of C is the absolute maximum, or I'll put in parentheses, global maximum of F on I if f of C is greater than or equal to f of x for all x in I. And similarly, f of C is the absolute minimum or global minimum of F on I if F of C is less than or equal to F of X for all X in I. In either case, C is called an extrema of F.
I have a question.
Yep, fire away.
Are these intervals, are they closed intervals or open intervals?
Doesn't matter. Great question.
Because I was kind of thinking like if it's an open interval on both sides, then isn't there cases where there isn't a absolute maximum and absolute minimum?
Absolutely.
Okay.
So notice this does not say that an absolute maximum and an absolute minimum exist. It only says that if F of C is greater than or equal to F of X for all X in the interval, then that point, that C value is an absolute maximum. And now
Okay.
this gets kind of tricky with you because of the fact that the inequality here is greater than or equal to or less than or equal to, you run into a situation where what if it's a constant function? Then is every point an absolute maximum and absolute minimum? And at that point, we just kind of say, yes, that fits the definition, but also kind of no, it's one of those weird in between things. But we don't want to eliminate the possibility of having multiple absolute maximums that are the same maximum on intervals. And so if we think about like trig functions, right, think sine and cosine, those have absolute maximums of 1. They have an infinite number of them. And so they all are the same maximum value.
Okay.
Now, here is something called the come on, work pen. Oh. The extreme value theorem. It says if F is continuous on a closed interval. Oh man, my pen gonna die on me today. Interval AB, then F attains an absolute maximum value, F of C, and an absolute minimum value, F of D, at some numbers C and D in this closed interval A, B. So a big important piece here continuous. Okay. That is very important when we're talking about this section. Okay. If we are discontinuous even at a single point in A to B, then it is not necessarily true that these extreme maximum and these extreme values exist inside this interval. That's also the case if it's an open interval, then it is not guaranteed that these exist. So the function has to be continuous and it has to be on a closed interval for this theorem to apply. Now, another thing that gives us continuity, remember, is if a function is differentiable, right? If it's differentiable on an interval, that means it is continuous on that interval. Now, I'm going to do another definition, and this is just for local. The value f c is a local maximum if f of c is greater than or equal to f of x, and x is near C, and it's a local minimum if f of C is less than or equal to f of x, and x is near C. Now, this is very like kind of wish it's near C. What does that mean? What is it near? And it is exactly that. It differs depending on the functions, right? If a function has, say, some sharp turns, like say a sine function with a very short period, what near C means might be very close. It might need to be within like less than pi over 8, right? But if it's something like say a polynomial function that has zeros at like 2, 4, and 12, near C could be like within 1 or 5 or 6 of C. And so local maximum and local minimum are very kind of subjective based on the function. What we do get is that local maximum and minimums come on. Are always a turning point. So if we think back to the graph at the very beginning, all of our local maximum and global in that case were turning points. They're a point at which the graph turned. But if we consider closed intervals of graphs, we can get max and mins that are not a turning point. They're just the end points of our graph. Okay. So let's put that in writing. Endpoints of a function can be absolute max or min, but not local. And if we think of, so for example, f of x equal the square root of x plus 6. No, let's do x plus 4. Then x equals -4 is an absolute minimum. But not the local minimum. Does that make sense? If we draw the graph here. Right, this would be our f of x. This is -4. So we would say that -4 is the absolute minimum, but it's not a local minimum, because if x is near it on the left side, our function is undefined, and so we don't call it a local minimum. Functions can have infinitely many extreme values. They could have a max but no min, a min but no max, and they could even have none, right? And so I want to look at a couple graphs. Our first one here is, in fact, that is our square root of x plus 4. And so we can see that one has a global or an absolute minimum here. Absolute minimum. It has no maximum whatsoever. It has no local minimums. Now, if we were to create an interval, let's say we said the interval, closed interval from 2 to 4, then the endpoints would be the max and minimum points on that interval. We'll look at our next function. What is this function? What is this second function here? What's this function?
Sine?
Yep. This is sine of x. This has infinitely many maximums and minimums. If you look at our next function, we have some polynomial, even degreed polynomial, so both ends go up. This we'll say has infinitely many max mins. This has an absolute min, but no max. And this last one here has no absolute min or max. It does have local min and max, right? We've got locals here and here, but it doesn't have any absolutes. Does that make sense to you guys?
Yeah.
All right. So how do we find these? Right? With using derivatives, how do we find these things without just like okay, well, let me graph the function and then find it that way. We can find these using derivatives. And to do so, we have to define something called a critical point. A critical point of a function f with the number c let me be more specific, is the number c in the domain of f such that f prime of c equals 0 or f prime of c does not exist. So if we want to find the critical points of a function, we look for where its derivative is undefined and equal to 0. Any questions on that? So this is just a definition of what a critical point is. Now, this leads us into a famous theorem. It is Fermat's theorem. Not to be mistaken with Fermat's last theorem, which is a very famous, and I believe it's still $1 million problem, which in mathematics, there's some things called $1 million problems, which if you're able to solve them and prove that you're correct, they will give you $1 million. So Fermat's theorem says if f has a local max or min at C, oh, come on. And if f prime of C exists, then f prime of C equals 0. So what this tells us is that the derivative of a local max or minimum, if it exists, will equal 0. Now you may ask, well, when would it not exist? And if we think about the absolute value function, right? If we just think absolute value of x, the derivative at 0 doesn't exist. And yet it's a minimum. Okay. Now the converse of this is not necessarily true. Okay. Note, if f prime of C equals 0, C is not guaranteed to be a local max or min. And for an example, we just can think of simply x cubed. Right. X cubed. Because f prime of x, sorry, 3x squared, and f prime of 0 equals 0, but it is not 0, not a local max or min. Does that make sense?
Yeah.
Awesome. Anybody else? Does that make sense to everybody else? So what we've done so far is define a whole bunch of things, built a bunch of theorems, built a bunch of ideas up. And what it basically boils down to is to find maximum and minimum points. We take the derivative and then we look at 3 different things. And what we do with that is then we then check from the actual function. Find max and mins on an interval. We find the derivative. And look at 3 sets of things. Okay. Those things are 1, when the derivative is equal to 0. 2, when the derivative is undefined. And lastly, the endpoints of the interval. Now, not all of these are going to apply in every function. If we have open intervals or say no intervals, if it's just the domain of the function, we might not have endpoints. Not every derivative has undefined points, right? If our function is x cubed, right, our derivative is defined everywhere, so we don't have any undefined points. And so these are the 3 things we want to look for when we're trying to find these things. We may find them or not. And what we really just do is check the function. We can do that either by using the table, testing values of the function, or by simply graphing. Now you may be like, well, if I graph it, can I just see where they are anyway? And sometimes it's not easy to see where they are. I think about polynomial functions, right? We know how to graph polynomial functions based on the zeros, but we don't necessarily know how to graph them accurately enough to identify where the turning points are between those zeros. And those derivatives will tell us where those are at. So that's the whole purpose of using these things. Does anyone have any questions?
So the reason we set the derivative equal to 0 is because when like you're looking at a peak, it kind of goes to like decreasing to increasing, or like increasing to decreasing, and that point in the middle is when it switches.
Correct. So the maximum or minimum is the point at which the function stopped increasing and started decreasing, or stopped decreasing and started increasing, right? And for that infinitesimally small amount of time, the derivative, the rate of change, is 0.
Okay.
Let's look at some examples. Find the absolute max and min values for the following. So let's look at f of x, negative 2x squared plus 6x plus 5 in the interval from 0 to 4. So first thing we want to do is find f prime of x. So what is the derivative of this function? This one should be very easy for everybody, right? Especially after studying and taking that last test. Power rules should be a very simple process. We have negative 2x squared, negative 4x plus the derivative of 6x is just 6. 5 goes away. So now we need to solve when f prime of x equals 0. And that gives us x equals 6/4 or 3/2. Any questions on how I got that? So we have 3 possible extreme values. And they are x equals 0, 3/2, and 4. There's no point at which our derivative is undefined. And so we only use the point where our derivative is equal to 0 and the endpoints of our function. Now, knowing anything about fx is great. We know that it is a parabola. So we know that it's going to have a max and a min, or it's going to have one turning point and that's it. Now, to use this, we know that these are possible extreme values. So what we can do, because we're on this closed interval, is we can simply test the function at these points. And whatever it is what will be our max and min. So we're just going to test f of 0, f of 3/2, and f of 4. So to do that, we're just going to use our calculator. We have negative 2x squared plus 6x plus 5. Go to my table. We get f of 0 equals 5. Oh, f of 3/2 equals 9.5. And f of 4 is negative 3. So f has an absolute max at x equals 3/2 and an absolute min at x equals 4 on the interval 0 Does anyone have any questions on how we got that?
So you just plug them into the original function and see which number is the biggest.
Yep. See which one's the biggest, which one's the lowest.
Okay.
And the reason we can do that is because this function's continuous on this interval. And more so, it's differentiable on this interval. So we know there's no like sharp turns, right? No absolute value, nothing where it goes like just instantly just goes back down. So because of that, we can just find them and test them. It's really that easy. Okay. For this one, find all critical values and use a graph to determine any local max or min, and note any vertical tangents. So for this, our function is going to be a little trickier. X cubed times e to the x plus 2. So what's the first thing we need to do?
Take its derivative.
Take the derivative. So f prime of x equals, now if we look at this, it's a little more complicated, but it's actually really simple. Because that plus 2, the only thing that does is it just shifts our graph up, right? It doesn't affect the rate of change at all. And if we think about the derivative rules, we know we can distribute derivatives across addition and subtraction, right? So the derivative of x plus y is the derivative of x plus the derivative of y. So we can do that here, and basically the plus 2 goes away completely. So we can treat this function when we're taking the derivative of it as the same as taking the derivative of just x cubed times e to the x. And so this is just the product. So we're just going to take the derivative of the first. So we get 3x squared times the second plus the derivative of the second. And the derivative of e to the x is e to the x times the first. And we'll factor out. I see I have x cubed or x squared in both. So I can factor out e to the x, x squared e to the x times 3 plus x. Any questions on that? Are there any questions on this problem here on how we took that derivative?
Yeah, so you went from, on the right there, you went from x cubed, and then how did you get the 3 plus x?
So right here, so let me, so I have an x squared and an e. I have the x squared, I have the e to the x, I have an e to the x, and here I have an x cubed. So by factoring out x squared e to the x, this first one here, all I'm left with is a 3. And over here, the e to the x is out, that's gone. And if I factor out x squared, I'm still left with 1x. So I have that. Does that make sense?
Yeah. Thank you.
Perfect. So now, to find the critical points, we just simply want to find when f of x equals 0 or when f of x is undefined, right? Or when it doesn't exist. Is there ever a point when f of x doesn't exist or when it's undefined?
No.
Correct, right? We have x squared, that's defined everywhere, times e to the x, that's defined everywhere, times 3 plus x, that's defined everywhere. So this is defined everywhere. There's no issues with this being undefined, so we're all good. So now we just have to figure out when this equals 0. And to do that, we just use the product rule, right? Not the product rule of derivatives, but the product or the 0 product rule. So I have x squared times e to the x times 3 plus x. For that to equal 0 means one of those 3 things has to be 0. So f of x equals 0 when x equals, so what value of x makes x squared equal 0?
0.
0. Is there a value of x that will make e to the x equal 0?
I think if you let it go to negative infinity, but that's not exact value.
But that's not a value, right? So there's no value of x that will make e to the x equal 0, right? The limit of e to the x as x goes to negative infinity is 0, but that's not saying that e to the x equals 0. So nothing there will make that equal 0. What about x or 3 plus x? What makes that equal 0?
-3.
-3. So these are our critical points. Now what we want to do is we want to use the graph to determine any local max or min. So I'm going to stop sharing. Open my calculator up. And I'll share that. So our original function was x cubed times e to the x plus 2. And I'm just going to zoom 6, which is standard. We see this is what our curve gets. And now when x is -3, trace. So we can see our little cursor here blinking at -3. That is a local max, or I'm sorry, a local min. It could be an absolute min. We don't really know for sure on the left-hand side, but because there's no other critical values, it's safe to assume that is, in fact, an absolute max or minimum. That is an absolute minimum. Does that make sense? And then if x is 0, your cursor blinking there, is that a local max or a local min? Or neither?
Neither.
It's neither, right? Because we can see our graph levels out there, right? It's increasing, then it flattens out, obviously, because the derivative is 0, and then it continues to go back up. So that is neither a local min or a local max. It is just a critical point, and that's okay. So let's go back to our notes. And so what we have is that x equals -3 is a local minimum, and x equals 0 is neither. It's a what we call a saddle point.
I have a question.
Yeah, go ahead.
Could we tell from the beginning that's neither because we have an x cubed?
No, not necessarily.
Oh, okay.
Because, right, we could think of, I'm just going to kind of sketch this out, right? An x cubed function could look like this, right? That would be a cubed function as well. And that has both min and maxes, local mins and local maxes. So we're going to do one last problem together. We're going to do the same thing. Erase this. Now let's let f of x be the cube root of x squared minus x. So we need to find f prime of x. To do that, I want to first say that f of x, instead of the cube root of x squared minus x, I want to think of this as x squared minus x to the 1/3. So now we can use chain rule to get that f prime of x. And you may have been able to do this just from what we were looking at before. And so the derivative, we get 1/3 times x squared minus x raised to the negative, or not negative, raised to the 2/3. Then times quantity 2x minus 1. Does everybody see how we get to this point?
Yes.
Okay. So I'll clean this up a little bit. I'll bring that 2x minus 1 into the numerator. So we have 2x minus 1 over 3 times the cube root. Don't do that parenthesis. Of x squared minus x squared. So we need to find when f of x equals 0 and when f of x is undefined. So f of x equals 0 when 2x minus 1 equals 0. So that is when x equals what?
A half.
A half. And f of x is undefined when 3 times the cube root of x squared minus x squared equals 0?
0.
Is that it?
One.
0 and 1. So 3 times the cube root of x squared minus x all squared equals 0 only when x squared minus x equals 0. Well, that's just x times x minus 1. So it means x equals 0 and 1. So f of x equals the cube root of x squared minus x has critical points at x equals 0, 1/2, and 1. Is everybody with me on that?
So for a summary, we found these critical points by setting the numerator equal to 0 and the denominator equal to 0, and the numbers we got were like critical points.
Because when we took the derivative, we ended up with this expression that was a rational expression. So we had something to numerator, something to the denominator. The rational expressions equal 0 when the numerator is 0 and the denominator is not. And they equal, or they're undefined when the denominator is 0 and the numerator is not. Now, I knew for this one that there was no hole in this function. So there's nothing that caused both numerator and denominator to be 0. So I just kind of skipped over it. So what I want to do is I want to use Desmos to look at this graph. We can use our graphing calculators for it, no problem. But Desmos is just a little bit cleaner. So let's graph x squared minus x to the 1/3. Okay, let's share my screen with you guys. And so if we zoom in on this and we look, when x is 1/2, we see we have a minimum. When x is 0 and 1, those are points where our derivative was undefined. So we have vertical tangent lines at those points. So those are neither minimums nor maximums, even though they were critical points. The cases that we want to be concerned with is if we look at something like absolute value of x, the derivative is undefined at 0, and yet that is a minimum. And so that's why we need to identify the undefined points for the critical values in derivatives. Does that make sense?
Yes.
So we don't want to just necessarily arbitrarily say if the derivative is 0 or if the derivative is undefined, then it's a vertical tangent. And we don't want to say if the derivative is undefined, it's this sharp turning point. It can be different things for different functions. And so we need to make sure what it is. Let's stop sharing. We'll share back to the notes one last time and finish this lesson out. So what we have are that is that f of x has a like, just need to write 2 more sentences, pen, come on. Bear with me. Has an absolute minimum at x equals 1/2 and vertical tangents, tangent lines at x equals 0 and x equals 1. Any questions on that? So I have extended the homework for 4.1 and 4.3. They were originally due on Sunday. They're now due Tuesday. To account for having, moved the lesson from Tuesday to today. I did the same thing for our next section, 4.4. I haven't moved 4.5 and anything after that yet because I'm just going to kind of reassess and I'll adjust later on as we go. So that's all set for you guys. You guys can go ahead and knock out this awesome homework. And that's it. Does anyone have any questions for me? Awesome, you guys. That's it. I'm done. You're done. We're all done. Have a great weekend. I will see you guys back in the classroom as normal classroom 107 on Tuesday. Have a great day, guys.
Thank you. Have a good day.